Now I've got another graph of a sine function, and we're going to look at a multiple scaling of the same graph. We can use the same graph to represent, in this case, 4 different things. Okay, so my first scaling I've written in white, theta is 2 pi at this point, where the phase is 2 pi. Okay, so the phase at this point is always 2 pi, remember. So the phase is always 2 pi at this point. And theta then matches the phase. And it does here as well, but theta is something different here and something even different here. So the phase is always 2 pi at this point. And of course at the origin the phase is 0. So that we have a change in phase of 2 pi, which, as you know, corresponds to a complete cycle around the reference circle. Now, if I say theta equals 2 pi, then theta is the phase. So our sine function will be sine of theta, because again theta changes from 0 to 2 pi. Theta changes from 0 to 2 pi during one complete cycle. So we say that y equals sine of theta. Also, the white labeling, y is 1 here, and it's -1 down here. Now I've included y equals 1, y equals 4, but I've only written the -4 down here in green. And then in the orange labeling, I've written x equals 15 centimeters. You're not used to x being on this axis, but you might as well start getting used to it because we can put any variable we want on either axis. So x is 15 centimeters and -15 centimeters down here. 15 here, -15 here. Now don't let this confuse you. This has nothing to do with the x-coordinate on a reference circle. Okay. Since we're graphing the sine function here, since this is a graph of the sine function, it's clear that we're using the y-coordinate of the reference circle to do this. So we could let x be anything. It has nothing to do with the reference circle. And here x is 20V, which means 20 volts, -20 volts. So we have 4 different labelings of the scale of the y-axis and 4 different implicit scalings on the horizontal axis. Okay, I say the y-axis, I say the vertical axis, because this could be the v-axis, it could be the x-axis, it could be the y-axis. Okay, so anyhow, we've seen that if theta is 2 pi and y goes from -1 to 1, then this white graph just represents the function y equals sine of theta. Now, the green labeling, theta is 2 pi here, so that y is going to equal something, and it's going to involve, again, sine of theta, because theta goes from 0 to 2 pi on the graph, and that corresponds to a complete cycle on the reference circle, complete circuit of the reference circle, complete arc all the way around. Okay, however, y should be 4 here and -4 here. So how do we accomplish that? Well, we simply multiply the values of sine theta by 4. Since the sine of theta takes values from -1 to 1, y equals 4 sine theta will take values from -4 to 4, and we've matched up our conditions, our labeling, with our function. Okay, now what if t equals 2 seconds? Well, we can concentrate on the scaling of the horizontal axis. By now, we should understand that if we go from -15 centimeters to 15 centimeters here and here, then y is going to be 15 centimeters times the sine of something. What's that something? Well, that's something has to complete 2 pi radians when t changes by 2 seconds. So get a little sloppy with my writing. 2 seconds okay, what is the phase going to be? And I say theta changes by 2 seconds. I really should correct that to say that the phase changes by 2 seconds. Just more general to talk about the phase than about a specific phase changes by 2 pi radians. Okay, so how do we get the phase to change by 2 pi radians when t changes by 2 seconds? You should pause and think about that in terms of what you saw in the preceding video. So the phase equals what? The phase equals okay, now I've written down pi times t, but I'm going to erase that in a minute. And why would I want to erase that? Well, first place, if t changes by 2, then the phase changes by 2 pi. So what's wrong with this? Well, what's wrong with it is that t doesn't change by 2. T changes by 2 seconds. So the phase has to be I'll write the radians here since I'm going to write something to deal with that seconds. Pi radians times t. Well, if t is 2 seconds, then you got pi radian seconds. So we better have a second down here to divide the second that we have on our time t. So here's our phase, and now y is 15 centimeters times the sine of the phase equals 15 centimeters times the sine of pi radians per second times t. I'm going to rewrite that over here because I'm going to relate each of these functions to the graph. So if you can't quite read that, I can't blame you. Again, I didn't plan spacing very well, but there it is. Okay, now, what if t is 1/60th of a second at this point, and x goes from negative 20 volts to 20 volts? Well, voltage, and I've got x equals 20 volts. Okay, I really don't want that to be x. I'm going to want that to be kind of a fancy E. Little loop up here, badly written, but I'll write it a little better here, I hope. And this stands for electromotive force, and this corresponds to a voltage supplied to a circuit. And the voltage is such that it goes through a complete cycle in 1/60th of a second. That would correspond to the frequency of the power you get from the power station. Okay, so we would have electromotive force, you don't have to remember that word, equals, well, the amplitude is 20 volts. V stands for volts. I don't want to write it out, don't have room. So it's 20 volts times the sine of something. Now, times the sine of what? Well, phase change 2 pi radians, and I'm going to write out the radians simply because I want to write out the radians and the seconds when I do this unit here. Okay, so imitating what we have, so the phase is going to equal what? Okay, think about it. Okay, what would drive us through 2 pi radians of angle in 1/60th of a second? You can do this by inspection. There are other ways to do it. But I'm just going to say when the phase is 120 pi, radians per second times t. You can verify that if t is 1/60th of a second, then you're going to get 2 pi radians out of this. So that this equals the EMF, electromotive force, is 20 volts times the sine of 120 pi radians per second multiplied by t. So now I can label this graph. Okay, this could be the graph of y equals sine theta. It could be the graph of y equals 4 sine of theta, if we use this labeling. Okay, if we use the orange labeling, then y equals 15 centimeters times the sine of pi radians per second times t, and the purple labeling would give us, and let me correct this, it's not y anymore, because the orange labeling is for x, and I've also got to change this y to an x, being a little careless. Okay, so that's x equals this, and down here we have not y, but my electromotive force symbol's getting better. I haven't written it in a while. I've talked about it, but I haven't used the symbol. Times the sine of 120 pi radians per second times t. So the same curve could stand for this graph, or the same curve could stand for this function, this function, this function, or this function, according to how we label the axes.